Okay, my name is Jan Zalasiewicz. I'm a geologist, and within that I'm a stratigrapher, which is, I look at the history of the Earth from evidence in the strata. It's useful because, like all stratigraphy, it gathers together a lot of evidence of different sorts and packages it up. It kind of integrates it into what emerges in the head, at least, as something like a unified signal of the totality of change, the rate of change, and the scale of that change compared with things that we try to understand in the past. The Anthropocene is significant on a scale of Earth space and on the scale of Earth time as well. Okay, this is, if you like, an introduction to what the Anthropocene is geologically. It was proposed by an atmospheric chemist as a geological term, and it's travelled widely since then, so I'm going to try and take it back to its roots in terms of what it might be in Earth history. Earth history is something that geologists are blessed or cursed with. We have, sorry, is that better? I'm staying there. Okay, we have 4.5 billion years to cope with. And the only way we can stay sane is by being exceedingly bureaucratic about things. There is 4.5 billion years, which is parcelled up into units, each defined at length, after many arguments, by commissions and subcommissions and working groups, into units of time which we can function with. And there are quite a lot of them, and the work is still ongoing defining these, but it enables us to work and navigate within Earth history. This is where we are at the moment. So we are formally, technically, within the Phanerozoic eon, which started over 500 million years ago when creepy crawlies arrived on the world. And within that, there's the Cenozoic era, which started about 65 million years ago when the dinosaurs and much else died out. And if you like, the modern biology started, dominated by mammals on land. Within that, we're within the Quaternary period, which is, if you like, the last 2.5 million years of a bipolar glaciation, a lot of ice north and south. The ice ages in the vernacular. And within that, we're just at the very, very top of that. We're in the last 11,500 years, which is the Holocene epoch, the last of many interglacials, which was only defined formally about 5 years ago, or its base was finally placed. But the question is, now, are we in another epoch of time, geologically? It's not a new idea. It's been around really since geology has been around as anything like a formal discipline. In fact, this is probably before the word geology came in. The first Earth history textbook, science-based textbook, was by this man, the Comte de Buffon, writing before the French Revolution in the 1780s. He wrote a book called Les Époques de la Nature, the Epochs of Nature. He had an Earth history, 75,000 years long to him. He thought that was enormous. He thought his audience would not understand it. Think of it in terms of money, he said, and maybe you will understand. It would have worked for the aristocracy, I think. And his seventh epoch was lorsque la puissance de l'homme a secondé celle de la nature. That means when the power of humans assisted that of nature. He thought the earth was freezing and that our burning of coal would put off the evil day by maybe a few 100 or 1,000 years. There were other people as well, George Perkins Marsh, the first American environmentalist, Antonio Stoppani, a rather remarkable Italian geologist, who coined the term the Anthropozoic era in the 1880s, Vladimir Vernadsky, who redefined, defined really for the first time in its modern sense, the biosphere, and again saw that humanity was affecting the geology of the Earth. But really, those ideas, geologists, my tribe, thought they were nonsense, basically. What they said was that humans think they're doing big things, but look at continents, look at volcanoes, look at oceans opening and closing, look at mountain belts raising. That is geology. You know, so this superficial stuff is insignificant on that scale. And when I was a student, and throughout most of my professional career, that was really the case. That idea began to change, and the man who crystallized it was Paul Crutzen, the atmospheric chemist, who won a Nobel Prize for his work on the ozone layer, depicted as a superhero in the new Deutsches Museum exhibition due to open soon on the Anthropocene, with some justification. You know, he has done some remarkable science, and he has driven the idea of the Anthropocene as something special in geology. Since then, it has, because we're geologists, we're bureaucratic, we're formal, we're pernickety, we have set up, you know, the idea was discussed by a group I was involved in, the Stratigraphy Commission of the Geological Society of London, where, somewhat to my surprise, and probably after a working lunch, 21 out of 22 of us decided not that it should be formalized, but that it was worth investigating with the potential view to formalization. We move very slowly and very carefully. The time scale is very important. It's a backbone of our science, so we do not, you know, treat it lightly at all. So since then, there has been a formal working group of the International Commission on Stratigraphy, the people who decide the time scale, and a lot of rather heavy, tedious papers on what the Anthropocene may be or may not be in different ways. Here's one collection a couple of years ago from the Royal Society. There'll be another collection from the Geological Society of London out, hopefully this spring, giving the evidence, the geological evidence for the Anthropocene. So what is it, really? This is, if you like, Paul Crutzen's idea of it. So we went through, there's the last 15,000 years, again we deal in these kind of diagrams, as Libby said, these strange cartoonish pictures. 11,000 years ago, the world changed. The ice melted, most recently. Temperatures rose, stabilized, sea level rose, stabilized. And we have been in something like the most stable environmental period for the last, I don't know, 300,000 years or so. And that has allowed us as humans to develop a stable civilization. Then, roughly 200 years ago, things started changing sufficiently to impact the planet visibly and uncontroversially. There have been effects before then, but the Industrial Revolution is when human population rose above 1 billion. It's now 7. Carbon dioxide began to rise. It's now risen a lot, and so forth. Looked at in more detail in this is where the great acceleration comes in. And this is a strong candidate. If the environment started in 1948, there's a good argument to say that that's within a couple of years of when the Anthropocene stratigraphically may be said to have started. Not maybe historically or in terms of any of the science, but in terms of stratigraphy, a dividing point in Earth history. And geologists need these dividing points. So what is the evidence of the Anthropocene? The way we go about it is we take, if you like, environmental change and we dress that in geological terms, rocks, minerals, fossils, the kind of things that we understand in our blundering kind of way. Minerals, rocks are made of minerals. What have we done with minerals? Well, one of the things we've done is to create things which have not been around for 4.5 billion years of Earth history, through all of those previous eras and periods and epochs. Metals, almost all metals in nature, with a few exceptions like gold, for instance, are combined with other elements to form compounds and minerals. Humans have taken things which were almost unknown in geology, like aluminium, have made an awful lot of it. Titanium, likewise, vanadium and molybdenum, lots of other things unknown in nature. We've separated these things out and produced them in hundreds or thousands or tens of thousands of tons. To the extent, for instance, that, let's say, aluminium, one of these things, again, its growth started in about the mid-20th century. And since then, we've produced something of the order of 500 million tons, which is enough to coat the United States of America and a bit of Canada in standard aluminium kitchen foil. This may or may not be a bad thing, but it shows the scale of the kind of things in minerals. And lots of other things. There are synthetic compounds of all kinds. Borazon, the one at the lowest. Harder than diamond, synthetic boron nitride compound. Manufactured now in hundreds of tons as an abrasive. Lots of synthetic garnets to make lasers with. The ballpoint pen, tungsten carbide, also unknown in nature. How many ballpoint pens are there? At least 100 billion of the big crystal ones. That much, Wikipedia says. Carbon fiber, graphene, mineraloids. Here, these things, ceramics, glasses, again, made in very large amounts. Plastics, made in large amounts and rarely recycled. So how much of this is there? The problem is nobody is counting any of this. One can work out, if you like, a history of minerals growing on Earth. There is an evolution of minerals from about a dozen in outer space to about 250 in a growing around an accretion disk, around a star in meteorites, to about 1,500 on a lifeless Earth, to about 4,000 when oxygen comes in and gives an oxide and hydroxide for everything. Since when it's been stable, we have probably created another few thousand. Nobody is counting. The materials chemists maybe know, the geologists don't yet, but it is a significant geological departure. Minerals make rocks, and we make things like this, concrete. Again, something of the order of, again, I've tried to check the numbers. Google says anything between 2 and 8 billion cubic meters per year now of concrete. Bricks, 1 trillion bricks per year, roughly. So this is, again, enough to create very large, tangible amounts of new rocks which have not existed, for billions of years beforehand, which are distinctive geologically and which are now present in very large amounts. Rocks make strata, and of course we deal with strata. I'm a stratigrapher. Strata are things which you can say you can pile up on the ground. So we pile lots of materials, rocks, including the new minerals, up on the ground surface. We make holes in the ground also, which we take rocks out of. We create barricades like the Aswan Dam here and trap sediment behind that. Now, all of that geologists can take and map as strata, and they've been doing it. Even the days when I was a working mapping geologist, we were doing that. We were mapping these kind of things on geological maps. And so here's a recent one of London, and you can see the proportion of London that is made up of these sorts of geological categories called made ground, the stuff that piles on the surface, worked ground, the holes in the ground, and infilled ground, a rather complicated mixture, of the two. And we've gone beyond that also. We have burrowed more than any other creature by orders of magnitude. The deepest burrowers in the sea are probably things like the Callianassa shrimps. They go down about 4 meters and create burrow systems. On land, foxes and wolves do something like the same. There has been one example of a dinosaur burrow recorded going down about 1 meter. We go down commonly hundreds to thousands of meters. We either take out whole strata, whole coal seams. We can go down 5 kilometers. This is 5 kilometers down in South Africa in a gold mine. And this is a picture of us not personally going down, but sending our drill bits down into an oil-filled reservoir. The total length of boreholes drilled just for oil in the world has been estimated, and somebody's put some work into this, which I don't envy, as about 50 million kilometers. 50 million kilometers is roughly the total length of our surface road network. It's roughly the distance that separates us from the planet Mars. And this sort of stuff, once we drill it in the Earth, those marks won't go away, not for hundreds of millions or billions of years. We've done something else that biological species have never done. This is a part of the crater of one of the A-bomb tests, on the Yucca Flats in the States. You can see the road and the trucks leading up to it. About a kilometer beneath that, there is a large mass of rubble which is melted. We're creating something like a small to medium-sized granite pluton in the Earth. Again, this is geologically quite extraordinary. We've gone from land to sea, and again, one of the things we've done, again, particularly in about the last 70 to 80 years, since we've had lots of power from oil, is we've trawled. We take trawlers, these heavy-weighted nets. You can see the scale of it there. And virtually all of the surface of the continental shelves have been trawled. So it's a greater proportion relatively to the land surface. We've ploughed about 40% of the land surface. We've ploughed in excess of 90% of the continental shelves now. And the marks are quite striking. Again, you can see the sort of marks there. It changes the sediments. It changes the life there. We've gone down on the far left, that landscape there is a kilometer down. It's a set of submarine canyons. You can see the scale there in kilometers. And those, the ploughing there, they're ploughing for edible shrimps. They're trawling, and it has completely smoothed the landscape. It's again remarkable and very preservable in terms of geological things. Anything in the sea we do tends to survive as strata, into the far future. Chemistry. Chemical changes we call chemostratigraphy. Layers of strata marked off by their chemistry. One of these is very well known now to us all. It's how Earth is warming. Of course, we need energy. We need lots of it. Most of it we get from carbon, and we need, and this has been growing remarkably. With this, it's quite easy to change the composition of the oceans and atmosphere. This is a lovely image. It's not made by a geologist. We're envious of that. It's an artist, Adam Neiman, who on the far side there took all of the air of the Earth and wrapped it into a ball at atmospheric pressure, and there it is, that kind of opaque ball. Further on that side, there's all of the water of the Earth. Again, into a ball, that little marble, excuse me, rolling about on North America is all the water we have. So it's quite easy to change the composition of both. And so we are doing. There is carbon dioxide, the Keeling curve, the iconic curve with carbon dioxide levels rising. We now know that that is, again, extraordinary in terms of history because of evidence from this kind of thing, from ice. This is part of an ice core drilled from Antarctica. Now the drills cores reach back about 4 kilometers and about 870,000 years into time. We have fossil air. And the fossil air clearly shows that CO2 levels have gone up and down very regularly between 180 and 280 parts per million of carbon dioxide. And since 1800, and particularly again, since that 1950 mid-20th century date, it's gone up by roughly the difference between a glacial and interglacial phase of the ice ages. And of course, what again the ice cores tell us
is that the temperature and CO2 go up and down in lockstep in history over 100,000 year and 10,000 year time scales. So currently CO2 has gone up, and because the Earth is a complicated system, it takes a little while, decades, centuries to react, but nevertheless temperatures do appear to be beginning to catch up with the CO2. Various effects of that. One of the biggest effects is that, of course, as CO2 increases, it is a greenhouse gas. That's been known since John Tyndall in, 1870 something. And so ice is beginning to melt. Again, we can just about begin to measure that with satellites. Again, we have just a few years' worth of satellite readings from north and south. And both Greenland and Antarctica are losing mass by many millions of tons a year so far. Sea level is beginning to creep up, and say it's creep up. It's only 30 centimeters in a century. That's geologically insignificant. So by the end of this century, the kind of forecasts is about a meter sea level rise. Again, that's geologically insignificant. Libby said, 120, 130 meters is the glacial interglacial sea level rise and change. And that is the kind of scale that is now geologically significant. But insignificant geological changes are, of course, significant to us as humans because so much of our infrastructure is out on near sea level. So there's Botany Bay with a 1 meter sea level rise and showing the beginnings of flooding there. The areas around Newcastle there also showing that. We can take that a bit further in Britain. There's a flat area called the Fenland, not far away from where I work in Leicester. And there have been a set of simulations of what's going to happen with 1 meter, and then 2 meters. That's probably another 50 years after the end of the next century. 3 meters, 4 meters, 5 meters of sea level rise. Again, because a lot of our land surface was built in the Holocene, it's near sea level. So small amounts of sea level rise, geologically trivial, will flood a lot of the landscape. After that, it's less change. So there's 9 meters, and Swaffham, still you can live in Swaffham still quite happily. 20 meters, you can still live in Swaffham. You melt all of the ice, and you get to 60 meters, you can still just about live in Swaffham then. I live at about 70 meters. I will have a seashore, with that, or my great-great-great-grandchildren will. Okay, other signals. The other CO2 problem, of course, is we dissolve CO2 in the rainfall and in the oceans. That is lowering the pH of the oceans, as CO2 levels rise in air and sea. That kind of thing has happened before in the past. There have been ancient global warming events. There's one 55 million years ago, drilled from the bottom of the ocean, and at that 55 million year level, the seafloor literally dissolved. You can see that the difference between chalk, calcium carbonate below, and dark silica above. So that is the kind of thing we threaten if we carry on. And of course, before that happens, we'll make life uncomfortable difficult or impossible for the creatures which need to make their skeletons out of calcium carbonate. Corals are probably going to find life difficult at 550 parts per million and begin to shrink instead of growing. And that is, again, kind of end century with business as usual. Other things, other chemical signals, phosphate, that's been mentioned also in Libby's talk. And of course, phosphate is one of the things we need. We need there are a lot of people, we need a lot of food, we need to stay alive, and that's been a constant problem. In the UK of the 19th century, population was expanding, the farmers were struggling to keep up. Turnips was one of the great inventions. And it was great, but they needed feeding. And people realized that if you, by graveyards, things grew better. And so bone was good, so they took all of the animal bone from the slaughterhouses, not enough. And so then gangs of workmen, of labourers, went from England to Europe and scoured the battlefields. And at one point, we're taking back 3 million skeletons, 3 million cadavers a year, to recycle, to help feed the English. Justus Liebig, also mentioned, said England was a vampire hanging on the neck of Europe at that stage. It still wasn't enough. So here's another industry that started and took the bones, not of people this time, but of dinosaurs. There are layers of rock around Cambridge and elsewhere with dinosaurs. So they took those dinosaurs and ground them up. It was a big industry. Dinosaurs and dinosaur poo as well, coprolites were used in that. Still not enough. So here's one thing. It's an ancient Egyptian mummified cat. Again, in 18-something, they found a cache of 180,000 mummified cats. The ancient Egyptians didn't throw anything away. And those, again, were taken into England, ground up, and spread on the fields. Here is a cartoon from Puncture of the Cats getting their revenge on the farmers. And, of course, we still have a phosphate problem now in trying to get enough of it. Nitrogen, we don't have so much of a problem because of the harbour process. We can take that from the air. But we use a lot of it. That shows up. So we have, the nitrogen revolution is one of the big geological revolutions. There may have been nothing quite like it for about 2.5 billion years since the Proterozoic era. And it's showing up. There's, all these diagrams, these graphs. The inflection of that is about 1950, when the aerosols from nitrogen begin to impact upon distant lakes, distant from civilization. Another effect is the dead zones. We feed our crops, we feed the land. Some of the nutrients, of course, much of the nutrients is washed into the sea that feeds the plankton. The plankton die, and where the water is shallow and sluggish, then in those seas, come the summer when the water is still, over hundreds of thousands of kilometers now in the Baltic Sea, Chesapeake Bay, the Gulf of Mexico, and so on, everything dies on the seafloor. And these are the dead zones. Again, geologically not new. Again, these are dead zones in the Cretaceous, these dark lines in the chalk, that's about 100 million years old. So we are beginning to repeat some of the hothouse climate phenomena in that. Other signals, of course, the chemical signals, the radionuclides in there. Life, again, paleontologists study fossils, so here are some fossils. We have body fossils, we have traces. Here's a trace of a creature crawling on the sea floor. Here's one of our traces. Here's another trace. This is a fossilized wasp's nest. It's about 1 million years old from Tenerife. This is our equivalent of it, or one of our equivalents. This is a human trace fossil, which we make into big systems. And here's a part of a big system called Shanghai, an urban stratum or trace fossil system. Very big, very solid, and which goes on and on and on and on. It goes, spreads across the fields, of course, into a rural trace fossil system covering about 40% of the landscape. Body fossils, again, we're familiar with these, the big ones and the small, cute ones, which, of course, tell us a history of periods of radiation and periods of extinctions. There's 500 million years, life going up and life going down. Is life currently going down? Well, there have been extinctions. The dodo, the Yangtze dolphin, about, 5 years ago, probably became extinct. The Costa Rican golden toad, becoming discovered 1964, I think, extinct roughly 1990. Are we at a mass extinction event? Well, Tony Barnowski and his colleagues tried to answer this a couple of years ago in Nature. Has extinction arrived? Not yet. The number of species extinct is still only in a few percent, but the number of species critically endangered is in the few to several tens of percent. So we're on the edge. They estimated business as usual without the effects of climate change, with something of 2 to 3 centuries, will give us a Cretaceous Tertiary style mass extinction event. We already have, of course, one biological phenomenon which again is unprecedented in geology, species invasions of, well known here, originally from Spain and then to Europe and then around the world, including to this continent, the rabbit, the cat, my cat controlling the ecology of my back garden, something of the order of 250 to 500 million of those are now around the planet. Rats, of course, everywhere. In the zebra mussel, originally in part of Russia, that spread and spread and spread and has taken over the United States, something the Politburo never managed in its time. And invasives now make up a very significant part of many countries, and they're here to stay. They like it. They're the survivors, and as many things will not pull through, these probably will. So, as a final measure, we can measure ourselves, if you like, culturally, spiritually, economically, but also simply by weight, by body mass. How do we measure up? We measure up currently in terms of terrestrial vertebrates to about a third of total land vertebrates. Most of the other 2/3 are the things we keep to eat, basically. Roughly 5% is the wild things. This is the cheetahs, the lions, the tigers, the elephants, the rhinos, and so on. And that is also, that's unprecedented, this dominance, of a few species. What's also unprecedented is, again, because of the nitrogen and the phosphorus, we've become so good at pushing nutrients into crops and taking those crops and feeding them into the things that we then eat, is that we've increased the number of land vertebrates in terms of biomass by something like an order of magnitude over what's called, if you like, normal baseline, normal geological times. And of course, our machines, are at least an order of magnitude bigger than that. So this is all in all quite a big phenomenon geologically, which we're still trying to come to terms with and to grasp. So really the question which we're still grappling with and trying to describe as best as we can is, are we living in the Anthropocene? Well, a couple of years ago, the Nobel Laureate Symposium in Stockholm used the Anthropocene, suggested it was a useful means to encapsulate, the state we find ourselves in. The journal Nature also suggested in an editorial that it was again a useful means to try and integrate everything that's going on, in an attempt to understand it. So are we breaking through to something really quite new here? So again, it's a question I leave you with a sunset as ever, but an Anthropocene sunset with the contrail up there in the sky. So thank you for your attention to and your patience with all of this bloody geology,